In this video, I'll explain the vSphere CPU scheduler and how it works to spread virtual machines across multiple physical processor cores. So let's start with some basic terminology. And these are key terms that I'm going to use throughout the remainder of this lesson. So first off, we have a world. A world is simply a thread of execution inside of an ESXi host. So a good example of a world would be a virtual CPU for a virtual machine. Each virtual CPU that I configure a virtual machine with is going to be a thread of execution on an ESXi host, and it's going to be represented in ESXtop as a world. So a virtual machine actually includes multiple worlds, especially if it has multiple processors. The number of worlds per VM is really going to depend on the number of processors, but there's also a world for displaying the mouse, keyboard, and screen. There's another world for the virtual machine monitor. So these are basically just processes that run for each virtual machine. And there's also worlds that are unrelated to virtual machines. So worlds for functions like vMotion, for example. So the worlds are basically just processes that my ESXi host is running. Then we have symmetric multiprocessor. So symmetric multiprocessor is a simple one. When you see SMP, what you basically want to think is this is what gives the ESXi host the ability to support virtual machines with multiple CPUs. That's really all it is. Symmetric multiprocessor, allowing a virtual machine to leverage multiple physical processors at once. CPU affinity, here's something I really don't recommend configuring unless you have a licensing requirement to do so. CPU affinity basically bonds a virtual machine to one specific physical processor. So that means that that virtual machine can't be vMotioned. That virtual machine can't fail over with high availability. CPU affinity is basically forcing it to use one particular processor. So I try not to enable that feature unless I have a licensing requirement to do so. And then finally, ESXtop. That's something that we'll be taking a look at in future lessons. So I'm not going to get too deep on it now, but ESXtop is a command line performance monitoring tool that I can use to analyze the performance of an ESXi host. And many of the measurements and performance indicators that I'm about to talk about here can be easily viewed in ESXtop. So let's start with CPU sharing. Here we see a diagram of an ESXi host, and the ESXi host has two physical processors, two CPU sockets. And each of them is a quad-core CPU. So I have a total of 8 CPU cores. Now I go ahead and I create myself a virtual machine and I configure it with 2 virtual CPUs. Each of those virtual CPUs is going to be assigned to one of these processor cores. So now I can see my VM is using 2 logical processors, using 2 CPU cores on this CPU socket. And if I boot up another VM on that same host, and this VM has 4 virtual CPUs, now that VM could potentially be sharing the same processor cores as the first virtual machine. So ESXi allows multiple virtual machines to share the same processor. It does so through a mechanism called time slots. What it basically does is allows these VMs to take turns with each other using that processor. So if I put too many VMs on the same host, they're not going to work quite as well. I don't want too many VMs sharing the same set of processors and pushing them too hard. So you should always be striving to hit that ratio just right. You want to make the most out of the processors you have. You want them to be 60, 70% utilized, but you don't want them to be 90% utilized and spiking up to 100% because then your virtual machine performance is going to suffer. So that's our first key concept in this video. Virtual machines can share the same physical processor cores. So now that we've learned that a virtual machine can share physical processors with another virtual machine, here we see two VMs, each of them configured with two virtual CPUs, and they're sharing the same processor cores. Although in this scenario, it doesn't really make a lot of sense. Why have these two VMs sharing these two processor cores when there's other cores available with nothing using them? So the ESXi host will actually do CPU load balancing under the surface. We don't have to configure this. We don't have to manage this. It just happens. So in this case, the ESXi host may recognize the fact that it could be more efficient and take that second VM and migrate it to these other processor cores. Again, you don't even see this happening. It's all done underneath the surface, and the ESXi host will automatically migrate VMs from one core to another to improve performance. If you've configured CPU affinity, this is not possible. CPU affinity pegs your VM to one particular processor. Now let's take a moment to talk about hyperthreading. So here you see two processors. On the left, we have a non-hyperthreaded processor. On the right, we have a hyperthreaded processor. So let's think about what the difference is between these two processors. Now, what I want to start out by saying is neither processor is more powerful than the other. So both processors basically have the same horsepower. They're both equally fast. They're both equal. The non-hyperthreaded processor, however, is less efficient. So with a non-hyperthreaded processor, VMs are essentially needing to take turns. The VM on the left sends an instruction. It gets completed. Then and only then can the VM on the right send an instruction and have it get completed. So there's actually some idle time, right? And if we watch this animation, you can see where the idle time is. So here, VM1 sends a command to this processor. It's completed. Now the processor is doing nothing, waiting for that second command to come in. So there's that moment in between those CPU instructions arriving where the processor is idle. Let's look at it one more time. First command gets completed. Now the processor is idle. Second command arrives. Now the processor is idle again. So what hyperthreading does is basically reduce that idle time. It allows multiple virtual machines to send commands simultaneously, like we see in this animation. And now, the moment that the processor finishes with the first command, the first instruction, it can immediately move on to the second instruction because it's already there, ready to go. The idle time gets reduced. So hyperthreading doesn't necessarily make your processor faster. What it does is it reduces the idle time of your processor and makes it more efficient. And that's really what makes a hyperthreaded processor faster. Now, what do you need to know about this in your environment? Well, you need to have hyperthreading enabled on the BIOS. That's really the big thing. If it's enabled on the BIOS, then ESXi can take advantage of it and leverage it. So just make sure that if you have a hyperthreaded processor, that hyperthreading is enabled on the BIOS. Okay. So now we're going to walk through some examples showing how the ESXi host shares CPUs. And we're going to start with the old way. So we have to understand the way it used to work if we're going to understand the way it works now. And so we're going to do a little history lesson here. This is called strict co-scheduling. And so with strict co-scheduling, in this diagram, we have an ESXi host. And the ESXi host has 4 processor cores. Right, so that's what we're seeing here is an ESXi host with 4 processor cores. And so here at the bottom of the screen, we see we've got 1, 2, 3, 4. Those are my 4 processor cores. I have a single socket quad core CPU. So any VMs that run on this host are going to share these 4 processor cores. And so here I have 2 virtual machines running on this host. VM1, which has 4 virtual CPUs, and VM2, which has 2 virtual CPUs. So virtual machine one starts executing something, it needs its processors. What's going to happen is virtual machine 1 is going to grab those 4 processor cores and say, I'm using these. And so for that particular time slot, the purple VM, the VM on the right, is out of luck. If it wants to use processors, it has to wait until the next time slot. And my orange VM, it needs 4 processors in order to work, so it has to wait till the next time slot, till the purple VM is done. And so what you end up with is 2 VMs essentially taking turns. Now it's my turn to use the processor. Now it's my turn. You have to wait. Now it's my turn. You have to wait. They're taking turns. So what we end up with here is some wasted time slots. We see these slots that are shown as wasted slots. Those are CPU resources that could have potentially been used. But because the orange VM needs 4 processors in order to function, it can't take advantage of those spare 2 time slots. So what we can end up with in this scenario is something called a high CPU ready value. So what do I mean by CPU ready? CPU ready means this. My virtual machine is ready to execute something. So let's say that the purple VM has something that it wants to do, right? It's ready to execute some sort of task. It needs CPU resources to do it. But in this first time slot, all of those CPUs are currently utilized. This VM has entered the ready state, right? It says, I'm ready. I need physical processors. And the VM is going to remain in that state of being ready until those physical processors are actually available. Then it can actually carry out what it needs to. So the longer a VM remains in the ready state, the worse off we are. We want low CPU ready values because that means a virtual machine is ready to do something but hasn't done it yet. Okay, so now that we've talked about the way things used to work with strict co-scheduling, let's talk about the way things are now with relaxed co-scheduling. Again, I have a single socket quad-core CPU, 4 processor cores, and again, I have the same 2 virtual machines. My orange VM with 4 CPUs, my purple VM with 2. And a similar situation occurs. The orange VM is using all of these cores in the first time slot. The purple VM has to wait. The purple VM may be ready, but it can't access any physical processor cores just yet. It has to wait until the next time slot. So far, it's really no different. Right? So far, it's really no different. Here's where the big change comes in. Now my orange VM can say, okay, the purple VM is using 2 time slots. I can take those other 2 time slots and use them. I can continue to make progress executing CPU tasks, executing CPU instructions, even though I can't get my full 4 virtual CPUs. And this pattern will continue. And so what we really have here is the big benefit of relaxed co-scheduling is the fact that we're not wasting those time slots. It's much more efficient. Right? But this introduces a different risk. This introduces a different problem called skew. So we can now run into a problem called processor skew or CPU skew. So when I configure a VM, like that orange VM, the orange VM had 4 CPUs. The operating system of that VM doesn't know what's going on in the background. The operating system doesn't know that those virtual CPUs are actually running on a physical CPU that's being shared across multiple systems. And so what my operating system expects is that when some sort of CPU instruction is kicked off, that all 4 of those processor cores will perform similarly. It expects those processes to be executed simultaneously. But if the ESXi host is not allowing it to use the time slots for vCPU 3, for vCPU 4, what's going to happen is those processors are going to start to get behind trying to execute those instructions. And if the difference becomes big enough, if a set of CPUs is making progress and another set of CPUs is not, this increases what we call skew, processor skew. And ESXi host has an acceptable threshold for this. So when that threshold is reached, the ESXi host will start holding back CPU 1 and CPU 2. They'll start limiting them. This is called co-stop. If you look in ESX top, this is expressed as co-stop. So if vCPU 1 and vCPU 2 are basically being throttled back, that's expressed as co-stop. So there's still problems. If you try and push too much work on these physical CPUs, there's still problems, even though we've kind of evolved since strict co-scheduling. There are still performance considerations that we need to think about here. Now, let's go back to our strict co-scheduling slide here for just a moment, because I want to talk about one other concept. I've mentioned you don't want to put too many VMs on the same host. You don't want to push too much work at one individual host because you're going to run into CPU ready. You're going to run into co-stop. You're going to run into these performance problems. There's another way that you can potentially relieve some of this contention. So let's say in this scenario, my orange VM is configured with 4 virtual CPUs. But let's say that my orange VM is currently using about 25% of the CPU resources that have been allocated to it, right? And maybe VM2, my purple VM, is using something closer to 70%. Well, I can solve all my problems right now with these two VMs because the VMs are improperly configured. They're not right-sized. VM1, my orange VM, it does not need 4 virtual CPUs. It doesn't need it. It's only using 25%. If I were to bring this VM down to 2 virtual CPUs, if I were to right-size it, now it wouldn't be using 25% of its resources anymore. It would be using 50%. Nothing wrong with that. Right? There's nothing wrong with 50% CPU utilization. So when I bring it back to 2 virtual CPUs, I'll see the CPU rise. For this VM, the CPU usage will rise to about 50%. That's going to have no performance impact on that VM. VM is going to work just as fast as it always did. As a matter of fact, that's actually going to improve the performance of my orange VM. And this is one of those weird concepts that people have a hard time wrapping their heads around. I can actually remove CPUs from the orange VM, and as I bring it down from 4 and bring it to 2 virtual CPUs, the performance will actually improve. And here's why. Now, VM1, when it needs to execute, it's going to try and grab 2 virtual CPUs. And when my purple VM tries to execute anything, it's going to grab 2 CPUs. These VMs don't need to take turns anymore. VM1 and VM2 each need 2 processors, and there's 2 processors open for them. They don't have to take turns. They can simultaneously use all of their processors at the same time, all the time. So by right-sizing, I've actually reduced my CPU contention. And by reducing the CPU count of the orange VM, I've actually made it perform better. And I've made the second VM perform better as well. I've reduced the likelihood of CPU ready, and I've also reduced the likelihood of CPU skew. Because now it doesn't have a vCPU 3 and a vCPU 4. It didn't need them. vCPU 1 and vCPU 2 are having no problem getting the time slots they want. They're executing simultaneously. So I'm not going to see that co-stop either. So it's really beneficial to right-size your virtual machines. If you're having CPU performance issues, that's usually step 1. Right? Is to make sure that my VMs are properly sized, that they're configured with the right amount of CPU. Okay, so now that we understand the basic concept of how the vSphere CPU scheduler works, let's talk about CPU contention. So we can use shares, and we'll see more about that later in this course. But I can use shares to determine which virtual machine takes priority. If one virtual machine has twice as many shares as another VM, that virtual machine is going to get twice the CPU entitlement of that other VM. And that's really how this is all broken down. The hosts carve up those CPU resources into time slots, and then the share structure determines the entitlements. So how much CPU time is each virtual machine actually entitled to? That's determined by shares. CPU ready time occurs when a VM is ready to execute against the CPU, but must queue that command. That's CPU ready. My VM is ready. The processor is not. So the VM has to wait. So there's some great documents that you can utilize to learn more about CPU performance in vSphere. The first document I want to show you is the vSphere resource document for vSphere 6.5. And there's a similar document for vSphere 6.7 if you're on that release. So as you can see, this document is going to walk you through resource allocation, like shares and limits and reservations. It's also going to explain CPU virtualization basics. So some of the stuff that we talked about here is covered to a certain extent. And if we click on the CPU virtualization basics, it's going to walk you through, I said, some of the concepts that we just learned about, like software-based CPU virtualization and performance implications and so on and so forth, and how to administer CPU resources as well. So it's going to walk you through multi-core processors and HyperThreading, which we just learned about, how to enable HyperThreading as well, CPU affinity, and so on and so forth. So this is a good document for some of those topics that we've been covering here for CPU. And it eventually gets into things like configuring virtual graphics and managing resource pools and DRS clusters, performance at a higher level. It also explains NUMA architecture. So if you have NUMA architecture in your environment, this is a nice document to kind of understand the implications of that. Now here's the other document that I want to reference, and this one's an oldie but a goodie. The CPU scheduler went through significant enhancements in vSphere 5.1, and some of what you see in this document is going to look very familiar. It's going to walk you through the difference between strict versus relaxed co-scheduling, which we just went through, CPU load balancing, migrating VMs from one processor to another. It'll get into concepts like NUMA migration as well, and how NUMA impacts all of this too. So it's a really great document. It walks you through the different CPU states like wait and ready and all of those good things to know. It walks you through strict and relaxed co-scheduling and the differences between the two. So if you're looking for more details on any of those sorts of topics, I know it's an old document, but it's a good one. The CPU scheduler in vSphere 5.1 is a great read to understand in depth what's going on under the surface with your CPUs.